Hello and welcome to this manufacturing process technology part 2 module 19. We were talking about electrochemical machining, and in context of that we had mentioned how this MRR or the material removal rate m dot could be represented by AI by ZF, where the mass removal rate, A is basically the gram atomic weight, I is the current in amperes, Z is 96,500, and I also told you how to arrive at this. It's a charge of 1 mole electrons, and then Z is the valency of the particular ion that is being electrochemically displaced. And from using the density term in the expression, we could actually calculate what is the volume removal rate, which is AI by rho ZF centimeter cube per second. Also, we were talking or discussing about, in real life we have really not single phases but alloyed systems where there are mixed materials, and then each of them would have a different density, each of them would have a different atomic weight, and it becomes a little cumbersome calculation wise to find out what is the dissolution density of an electrode made out of an alloy. So, I am going to now sort of talk about that aspect and give you a little more illustration into how an alloyed system can be worked out. So, when an anode let us say is made of an alloy, and instead of a pure metal, the removal rate can be found by considering the charge required to remove a unit volume of each element. Okay. And so, if the atomic weights and the valencies of the corresponding ions entering the electrolyte are, let us say there is a n atomic system, or there are different pure phases which are there in the alloyed electrode. So, you have atomic weight A1, okay, A2, A3, so on so forth, as the different atomic weights, so on up to An of the all participating pure phases, and similarly the valencies Z1, Z2, Z3, so on up to Zn. And also, if we assume that in the same using the same logic, that the composition by weight of the different phases 1 to n in the alloyed system is x1% of, let us say, A1, x2% of A2, so on so forth up to xn% of the nth phase, and we want to remove, let us say, a volume V centimeter cube of the alloy that would exactly contain let us say, because the total weight obviously of the alloy would be the average density rho average of the alloyed system. This is the overall density of the alloy in gram per centimeters cube times of V, which is the mass, okay. And so, xi percentage of this mass, in other words xi by 100, would be the amount of grams of the ith phase present in the particular alloy, okay. So, the if we consider how many moles of the ith phase are present in this much amount of mass in grams of the ith phase. So, I just divide this V rho average xi by 100 with respect to Ai, which is the atomic weight of the ith phase. So, these many moles are present, okay. That is how you find out from the grams to moles the how many moles are present, and each mole because it is a ith phase and it is containing a valency which is Zi, would have exactly Zi charges to be transported. So, I would say if I just this is 1 mole present, and then let us say if we have the electronic charge for 1 mole by just multiplying F with this, which means that this much charge is present times of Zi, because Zi is the valency, supposing there is a calcium plus 2 or a Fe plus 2 or a Fe plus 3. So, you have 3 electrons to mobilize 1 atom in case of plus 3 valency, you have 2 electrons to mobilize 1 atom in case of plus 2 valency, so on and so forth. So, this is a ith valent state having Zi valency. So, you should have exactly Zi electrons to mobilize the particular species, the ith species in the electrode, okay. So, in other words, the total amount of charge that is required to remove the ith volume, ith element in the volume V, which we have removed from the alloy, is actually given by this term here, V rho average xi divided by 100 times of ZIF by AI, okay. So, that is how you give the total amount of charge required. And obviously, the volume of the alloy removed per unit charge would then actually be equal to, if I had the total amount of charge of all the I elements added together, which I will actually in a more simplistically or in a more simplistic manner write here. So, we have, let us say, I phases, I varying between 1 to n, and we have from each phase contribution that is emerging is V rho xi by 100 times of ZIF by AI. Okay, so this is a sort of a sigma indicating that over the n phases how much total charge is needed, okay, to remove the volume V. And so I can have the volume of the alloy per unit charge, volume of alloy per unit charge as simply the volume V divided by this expression here. So I take out the V, the row average, the 100 and also F, okay, and so we are left with here I varying between 1 and n Xi Zi by Ai, okay, and so the V factor goes out and we are now left with just simply 100 divided by average density times of F times of sigma I varying between 1 to n Xi Zi by Ai, okay, Xi Zi by Ai, and I can actually further just change everything here by basically converting this 100 by F here, you know, into the corresponding value. You know already the value of F is equal to 96,500 coulombs, and so this finally comes out to be the volume per unit charge, you know. So this is volume of alloy removed per unit charge. So which is a very important term from a context of material removal rate in case of alloyed systems. So let us now look into a little more, you know, numerical oriented approach in order to predict some of these things. For example, if I were to just give you a small situation where in an electrochemical machining process there is a pure iron workpiece that is to be removed, and we wanted to find out what is the volume removal rate, what is the current that is required for a certain volume removal rate which has been given here. For example, the volume removal rate here given is 5 centimeter cube per minute. So the gram atomic weight valency at which this dissolution will take place are assumed to be 56 grams, valency is +2 valent state, and the density of iron is taken out to be 7.8 gram per centimeter cube. So having said that, if I just used the expression, let us say the Q dot or the volume removal rate here, which was centimeter cube per second, is 5 by 60 centimeter cube per second. Obviously this minute needs to be converted, that is why the 60 term times, or so this actually is equal to the atomic number A times, or atomic weight A times of I, the current, total amount of current which flows into the circuit, the electrochemical system, divided by the density which is 7.8 in this particular case, times the valency times Faraday constant 96,500. So we can just simply plug in the values 56 times of I, let us assume that we needed I amperes to do this kind of material removal, divided by 7.8 times of 2 times of 96,500, and so this makes I 2240 amperes. So you can think of that you are taking about 2.24 kiloamps in order to remove a small volume as small as 5 centimeter cube per minute, and so this gives a very high level of specific energy for this material removal rate, or you know, this kind of ECM or electrochemical machining process. So in the actual ECM, however, there are many other factors which would affect the removal. In fact, if I were to look at this similar example, you would see that the actual removal rates are slightly lower in comparison to the predicted removal rate, which is given by this solid line right here. And one of the reasons is that we have not really considered the other valencies which are there, and we have always considered the divalent dissolution in case of, for example, iron. But what happens in actual situation is that there may be also a trivalent dissolution possible depending on how many valency states exist. And so if that kind of a situation happens, obviously then you can't really predict whether an ion which is displaced is a trivalent or a divalent, and so actual removal rates are slightly lesser. So they vary slightly from the theoretically obtained removal rate given by this expression right here. Okay, so we now actually try to do another aspect here, which is also known as cyclic voltammetry, which is important for you to give a feeling that what is this as our oxidation or reduction that we are actually trying to find out. So you find out, you basically, if we look at this trend right here of a species which is actually getting reduced from an oxidized state, and we see that there is a plot that I am revealing here, which is between the current, okay, the current between the electrodes and the voltage that is being applied. So you see that there is obviously a certain voltage which is corresponding to the reduction potential of this oxidant species here, where there is a sudden release in the electrons and sudden absorption of the electrons, and there is suddenly a change in the current because of that. Current obviously is a positive charge, which is considered to be reverse of the electron flow which happens in a circuit, and that is how conventionally current is treated. So obviously, because of a sudden absorption of all the electrons together, the current has increased, because there is a again a whole movement, and so you can think of it that if supposing there is a plot of current which is going on at a certain rate and then slightly changed rate, near about this point where it corresponds to the reduction potential of the species, there would be a huge enhancement in the current, and which will be represented by a peak. So this is how most the reduction potentials of, or even the oxidation potentials as a matter of fact, are found out in species, and this is this term is known as voltammetry. So you can have either linear sweep or cyclic sweep, meaning thereby in a linear sweep you only oxidize or reduce, and in a cyclic sweep you do both of them together. So you have a backward voltage sweep and a forward voltage sweep, and you can increase the voltage per unit time between 2 volts, 4 volts, 5, 6 volts, something like that. So you have 2 volts per minute, let's say, or 1 volt per minute. So you're keeping on increasing the voltage as a function of time and seeing at what potential exactly the reduction or the oxidation of the species are going to happen. That is how voltammetry is performed on most of these species, and here we need to really find out that potential corresponding to which there is going to be a dissolution of the species, because it's a micro machine or it's a electrochemical machining that we are talking about. So we need to at least understand these standard reduction potentials, based on which we can actually put the location coordinates of our cell in terms of voltage current relationship. So when we talk about multivalent dissociation, obviously as the current is more, the dissolution takes place at higher potential difference, and there can be trivalent dissolution also occurring at a certain value of current, and at larger currents theoretical values tend to be more than the actual ones, because obviously there are going to be many other states which are also going to participate in the process of dissolution. Sometimes the dissolution valence also depends on the electrolytes. For example, copper dissolves in monovalent form of chlorine solution, whereas in nitrate solution the dissolution takes place in the divalent state. So this table here right here mentions some properties related to the different metals which participate in the oxidation reduction process, their gram atomic weight, the different valencies of dissolutions that they may possess, and the density that they have, and this is important for calculation sake, particularly on alloyed systems. And we are going to now look at a problem, an interesting problem of a multi-phase alloy called a mnemonic 75 that we want to find out for its removal rate in centimeter cube per minute. We have given that a current of 1000 amperes is passed, and we would now for now use the lowest valency of dissolution of each element, although there is a possibility that based on where the oxidation or reduction potential lies of the cell, there may be a divalent or a trivalent state which comes in. Okay, so I am not going into that complexity right now. We are just simplifying by saying that we use the lowest valency state in this particular case, and so we are actually putting together this composition weight percentage of the mnemonic 75 alloy. So let us say the removal rate, if we want to find out, so the removal rate in centimeter cube per ampere second or per unit charge has already been given by the earlier calculation that I showed you for Q is 0.1035 10 to the power of minus 2 by the average density rho average divided by sigma I varying between 1 and n. In this case, there are at least 7 phases that we are talking about. So, this n is actually 7, okay, xi zi by ai, where these i's are the ith phases properties, including the percentage weight, which is actually given here. Okay, so, this is the weight percentage of the particular species, ith species. The valency which we would be using is the lowest valency from the table earlier. I had just given you this table, right here, and lowest valencies are mostly, in this case, for example, nickel would have +2. Similarly, chromium would have +2 again, Fe is +2, so on and so forth. So, only the lowest values are being used for the valencies Zi. Ai obviously is the atomic number. So, let us now find out the most critical term here, which I would like to first get into, is the average density. Okay. So, first let us find out the average density, rho average of the alloy. So, rho average can be given as 100 divided by I varying between 1 to 7, okay, xi by rho I. So, I am considering here the overall base weight of 100 grams, and in 100 grams, as I have earlier illustrated, there are 7 species, each of them having different gram weights, like this is 72.5 grams, 19.5 grams, 5 gram, 0.4 gram, 1 gram, 1 gram and 0.6 gram respectively. So, what we are trying to do is to see that each of the phase has how much contribution in terms of volumes. So, 72.5 grams of nickel, for example, would have exactly volume equal to 72.5 grams by the density of the nickel. Okay. So, we just do the summation of that total volume of each phase, so that mass per unit volume can be calculated on an average basis. So, you have 100 grams divided by, let us now put the values of the different species here. We have 72.5 grams of nickel divided by its atomic divided by its density, mass density, which is 8.9 gram per centimeter cube, just borrowing it from this table. Okay. So, there is a density column here. For nickel we have 8.9 gram per centimeter cube. So, we do it for the remaining phases as well. I am not going to again and again refer back to the table, but just giving you the values here. 19.5 by 7.19 plus 5.0 divided by 7.86 plus again 0.4 divided by 4.51 plus again 1.0 divided by 2.33 plus 1.0 divided by 7.43 plus 0.6 divided by 8.96. So, the total average density happens to be equal to 88.15 plus 2.171 times of, so inverse of this into 100, whatever I am saying. So, plus 0.09 plus 0.43 plus 0.13 plus 0.07. Okay. So, this becomes equal to 8.18 gram per centimeter cube. So, the average density of this particular alloy comes out to be 8.18 grams per centimeter cube. Let us take this back to the equation that we had earlier or the relationship that we had earlier seen between the value Q, that is the volume per unit charge, and the average density. So, this is 0.1035 10 to the power of minus 2 divided by the average density, which is 8.18 borrowed from the previous step, times of 1 divided by this whole expression here. So, we have 72.5 times of the valency, the lowest valency Z, divided by the atomic weight of nickel, plus similar exercise for the other phases which are present, 19.5 into 2 divided by 51.99 plus 5 into 2 divided by 55.88 plus 0.4 into 3 divided by 47.9 plus 1 into 4 divided by 28.09 plus 1 into 2 divided by 54.94 plus 0.6 into 1 divided by 63.57. So, this in totality results in 0.1035 10 to the power of minus 2 divided by 8.18 times of 3.62. In other words, 0.35 10 to the power of minus 4, and the units here is centimeter cube per ampere second, meaning volume per unit charge which is being removed. Now, we already know that 1000 ampere or 1 kilo ampere current is used, the removal rate therefore would be equal to 0.35 10 to the power of minus 4 times of 1000, okay, times of, if I wanted to find this in centimeter cube per minute, just multiplying with 60, it is 2.1 centimeter cube per minute. Okay. So, that is how you can find out the volume removal rate Q dot, okay, of the alloyed system given the various components with the different weights and the different atomic weights and other properties associated with this whole setup. Let us now go into a little different problem about realizing what are the impacts of the different potential zones which are formulated from the solution to the solid electrode or vice versa on both sides. So, in electrochemical micromachining, when we are talking about the relationships between voltage applied across the electrodes, the flow of current, as we all realize, is not very simple. It is because the charge transport has to take place crossing the diffuse layer and the double layer, the Helmholtz layer, and then finally an interaction in terms of the charge transport into the electrode from the electrolyte and vice versa. So, the total potential profile would consist of the following. One is obviously the electrode potential, the other is the over voltage due to activation polarization. The electrochemical changes are in equilibrium when no current flows. So, the electrode potential acts as a barrier to a faster rate of reaction. So, an additional energy obviously has to be supplied to get the required MRR just because of this polarization, and there is a dual layer that has to be crossed by the ions, so that that particular potential has to be applied from outside. Okay, it is a sort of work done on the ion to cross over this dual layer. Then we have something called concentration polarization. Obviously, the ions migrate towards the electrodes of opposite polarities and causes a concentration, a super concentration of the ions near the electrodes. So, I think I had given a very clear illustration when we were discussing about this dual layer, that the concentration polarization, if you look at that the diffusion of the ion goes slower and slower as it goes near the electrode, and that is because there is going to be a accumulation of the ion of the opposite kind just near the electrode, and it creates some kind of an ionic barrier for the other ions to migrate. So, that is another polarization. So, you have a over voltage due to activation polarization when at the initial, and then obviously as the ions are migrating towards the electrodes also, there is some kind of a concentration polarization. Each ion has to pass through this concentration barrier to release its charge at the electrode, which is not easy. And then obviously there is a ohmic over voltage, which is because films of solid materials may form on the electrode surface, which offers an extra resistance to the passage of the current. And then finally there is an ohmic resistance of the solution itself from all these different barriers being crossed over, and then change of potential from the anode to the cathode. Okay. So, there is some kind of a ohmic resistance of the electrolyte which it offers, and it follows simple Ohm's law, but obviously the resistivity is too high, or the conductivity is too low from the solid to the solution. Okay. So, the ohmic voltage drop occurs across the bulk of the electrolyte. This is the main voltage drop and is only part of the electrolyte obeying the Ohm's law. So, if we were to plot all this on a voltage scale between a cathode surface and an anode surface, as has been illustrated here, so there would be some part of it which is the anode potential, some other part which is the activation polarization. There is of course a thin film resistance which happens because some deposition obviously would take place at the electrodes. It is called the ohmic over voltage, and then obviously there is a concentration because once the ion transport starts happening, there is a diffusion gradient created by concentration dc by dx at both the electrodes, and then finally there is a ohmic voltage drop, from one of the electrodes to the other that comes in. So this results in a sort of a anode over voltage and a cathode over voltage barrier, which needs to be necessarily crossed for getting into the ohmic zone for the electrolyte. So therefore, there is always an over voltage potential that has to be given, which is also known as this V minus delta V. This delta V has to be given in excess for the MRR to happen, because these potential barriers are always hindrances to the ion transfer process. So while doing electrochemical machining, you have to always obey the fundamental rule that there has to be not only the redox potential at which the dissolution will start to happen because of the oxidation reaction, the reduction reaction taking place simultaneously, but also you have to consider that in order to reach that potential point, you have to cross several barrier layers, and therefore slightly extra, slight amount of extra voltage needs to be provided for such barriers to be crossed over, so that you are exactly at that point where oxidation reduction can happen within the electrochemical machining apparatus. So obviously the total over voltage of an anode, if that is considered to be delta V and the applied voltage is V, the current then is given, actual current is given by V minus delta V by R. So this determines what is your actual MRR. You have to always make this substitution. In other words, this delta V, if you can provide ab initio, then you can get the MRR that you need at a particular current. So R is the ohmic resistance of the electrolyte. Now the conductivities of the tool and workpiece are much larger because they are metals, okay, and the conductivity of the electrolyte is not so large. Typically the electrolyte conductivity may be around 0.1 to 1.0 ohm inverse centimeter inverse, whereas if we look at something like iron, which can be easily the anode where the machining can take place, is about 10 to the power of 5 ohm inverse centimeter inverse. It is so huge, it is about 1 lakh times more in comparison to the conductivity of the electrolyte as such. Thus the surfaces of the tool and the workpiece can almost be considered to be equipotential. We are not really concerned with the potential effects that would happen because of disparities on the surface in terms of roughness, asperities or valleys, and so therefore we really don't, we consider it to be as far as our potential calculations at a macro level go, consider it to be atomically flat, but that is actually an assumption, because in reality when we talk about micromachining processes, and this goes to the lower scale, we have to consider even those asperities and the potential concentration effect that it would assume on the surface, which will result to a lot of differences in terms of machining that is going to take place. The conductivity of the electrolyte obviously is not really constant because of temperature variation, accumulation of bubbles, also a sporadic dissolution of the anode, which results in some small areas which would be islands, and I am going to talk about this in great details when we talk about defects in ECM. And obviously when we go to the micro level and do ECM, electrochemical micromachining, these factors have to be considered in great details at that time. So I would like to just end up this module in the interest of time, but in the next module we are going to do a little bit more about the understanding of how the two electrodes would behave with respect to each other. We can call this topic the kinetics and dynamics of the ECM process. So as of now, I would like to end this module. Thank you very much.